Aloha kako, and welcome to our live from NOIRLab at Gemini event. Thank you so much for joining us this afternoon. If you're here in Hilo, or later in the evening, if you are joining us from one of our other facilities. This afternoon, I will be happily presenting to you our host and our science guest. But first, a little bit of background about me. My name is Jamika, and I am privileged to be one of the outreach assistants here at the International Gemini Observatory here in Hilo, Hawaii. Today, I will be joined by two amazing guests. First is our host, and his name is Peter Michaud. Peter leads the communications, education, and engagement team for the Gemini Observatory as part of NSF's National Optical Infrared Astronomy Research Laboratory, NOIRLab. He's worked at Gemini for over 20 years, and before that, he taught astronomy in planetariums from the East Coast all the way to Honolulu. He will be joined by our special staff guest scientist, Nicolas Chene. Andre obtained his PhD in astrophysics from the Université de Montréal. He worked as a research associate in Victoria, Canada, then as a postdoctoral fellow in Chile for a few years before joining the Gemini Observatory in early 2013. His main scientific interests are massive stars and young stellar open clusters. So before we move over to Peter, just a few housekeeping notes. So we are on YouTube Live, and this is our first go through. So we are very much appreciative of your patience and understanding as we go through this. Now, of course, we are excited for your participation. So even as Peter and Andre are speaking, please feel free to go ahead and put your questions in the YouTube live chat. We do have another staff, Alyssa Grace, monitoring the chat so that all of your questions will be forwarded from there to us, to the host and our science guest, Andre, so that they can answer them. Peter will take questions at the end, but feel free to keep those questions coming. Additionally, there is a bit of lag time that can range from 5 to 10 seconds to maybe a little bit longer. So if you are having some issues with speech catching up, please accept our apologies on the front end as we are learning how to best use this technology. And without further ado, I'd like to go ahead and move to our host, Peter Michaud.
Thank you, Jamika, and aloha, everybody joining us. We're from, again, here in Hilo, Hawaii at the Gemini North. Normally, we do this program from our headquarters here in Hilo, but with social distancing, we're trying something a little different today. So we appreciate you helping us with this experiment to see how this works. Normally, we'd be doing this with a classroom of students or a group of students that we've been working with to share what we do at the observatory. So I'm going to switch over to my screen sharing mode. And let's see here, move my windows around a little bit. And we'll start off by taking a look at a few slides and videos to give you a bit of an overview of the Gemini Observatory, how things operate, talk a little bit about some of the science that we do and some of the exciting results and technologies that we use as well. So I'm going to start with a little video, time-lapse video that shows the Gemini North Telescope up on Mauna Kea here in Hawaii at night. And so you can see the stars in this time-lapse moving over as the dome points to different places in the sky. The Milky Way just, oops, and now we're jumping over to the inside view. And to just give you a sort of a sense of the scale of this, the telescope itself is about 7 stories high. And and you can see it tracking along. The sky is blue here. This is nighttime, but the moon is up. And if your eyes were sensitive enough, you'd be able to see the blue sky at night as well by moonlight. But the camera here is sensitive enough to show the color of the sky at night. The moon's about to set. It was a full moon, so as soon as the moon sets, the sun rises. That's what happens when the moon's full. Now we're going to just take a look at one more quick video here. We'll talk a little bit more about this later, but this is showing Mauna Kea, which is the tallest mountain on the planet if you're measuring from the sea floor. When you look at Mauna Kea, you're looking at it, you can imagine it's about waist deep in the ocean. About half of it is showing on the top, the other half is down underwater. So it's a big mountain, about 14,000 feet from sea level. And you can see as night approaches, the stars are going to come out. And again, the moon is lighting up the sky here too. And so you can see that you can see the clouds and whatnot. We'll talk a little bit more about this later. So I'm going to move on. I just want to say a little bit about the Gemini Observatory. We have twin 8-meter telescopes, which means the mirror that collects the starlight is 8 meters across. It collects an awful lot of starlight that way. And we have 2 telescopes. One of them is in Hawaii, in the northern hemisphere, about 20 degrees north latitude, and the other in Chile, somewhere down around 30 degrees south latitude, so that we can see the entire sky from the 2 telescopes. We're coming from Gemini North, which is in Hawaii, and here's a nice satellite view on a rare day when all of the islands are essentially clear. We're located on the Big Island, which is the one down in the lower right. I'm going to zoom in on the Big Island and take a look at a few features here. You can see those 2 big white caps in the middle of the, not in the middle, but on top and bottom of the island. That's Mauna Kea on the top and Mauna Loa down below, on the lower part of this image. And the white is snow. And we'll talk a little bit more about the weather and the environment on Mauna Kea as well. The other feature you can see in this image that's kind of interesting is over towards the right side of the island. You see a sort of a red glow there. I'm not sure how good the resolution is on YouTube, but if you look carefully, you can see that was actually taken a few years ago when lava was flowing from Kilauea. And you may recall that there was about a year and a half ago, we had quite a lot of other volcanic activity. We'll talk a little bit more about the geology here on the Big Island as well, just to give you a sense of sort of a perspective on where we're located here. This is our headquarters in Hilo. We get a lot of rain in Hilo, and that's why we like pictures with rainbows. You can see that we're an international partnership by the flags out in front of the building. At this time, nobody's in the building because of social distancing. We've closed the building and we're keeping it clean and ready to reoccupy, hopefully fairly soon. But our control room is there as well. And so at this time, we're not operational on the sky. We're looking at ways that we might be able to get back on the sky. But when we do operate, we operate remotely from a control room in Hilo. And at night, there's nobody on the mountain. During the day, typically we'll have a day crew up there that will be doing work on the telescope, up to a dozen or so people that will be maintaining everything, but they are also not going up the mountain right now to work on the telescope. Quick video here, just to, by the way, this is not to scale, in case there was any question about that. The 2 Gemini telescopes in Chile and Hawaii, both sides of the equator, that allows us to see the entire celestial sphere overhead. So we can see the northern sky, the southern sky, and collectively the 2 telescopes can access any point in the sky, which is a very powerful capability for an observatory to be able to see the entire sky. There's also some overlap, so there are objects that we can see with both telescopes. However, we very, very rarely would try to observe the same object with the same telescopes, unless there was some event that was happening that was changing very quickly, and we wanted to use the time zones to our advantage so we could see the object over an extended period of time. But that's not something we do on a regular basis. Of course, we have 2 telescopes. We're going to be focusing on the one here at Gemini North here in Hawaii, but this is Gemini South in Chile. You can see it's a beautiful, beautiful location there and beautiful skies. I will point out that the night this picture was taken, it did clear up and we had beautiful skies that night. It's not usually cloudy. And we don't like to show pictures of our observatories with clouds in the sky, but this was an exception. Speaking of clouds, I want to talk a little bit about the weather and the environment here in Hawaii. This is Mauna Kea looking at it from Mauna Loa, looking over during the day. This is a sequence of an entire day. I took pictures about every 30 seconds, and you can see what's called the inversion layer. See how the clouds come to a certain level and then level out and tend not to go any higher than that? That's one of the things that makes Mauna Kea such a great place for astronomy, is very rarely do the clouds get up to the top of the mountain and obscure our view. It's one of the reasons that here in Hilo, we get a lot of rain. Hilo's off to the right in this image here, so the clouds build up over us, dump all the rain on us, and keep it clear up on the mountain most of the time. Hilo gets, depending on where you are, about 150 inches of rain a year. So we're a very wet place. And it's fortunate because it's one of the reasons the top of Mauna Kea is so dry and such a great place for viewing the universe. There are some other features of Hawaii that people are quite familiar with. And one of them is the volcanoes. The Big Island is one of the most volcanically active places on the planet. And here you can see some of the eruptions of Kilauea. People often ask, well, if we have all those volcanoes, aren't we worried that Mauna Kea might erupt? Because all of the mountains here in Hawaii are volcanic in nature. It's been, geologists say, about 4,500 years since there's been volcanic activity on Mauna Kea. So we feel pretty confident and pretty safe on Mauna Kea. However, it's a long dormant volcano. It's not extinct. And so someday it will probably become active again. Mauna Loa, on the other side of the island, has been active in recent times. In fact, in 1984, there was a flow that got within about 5 miles of Hilo. You could see the glow from Hilo. And Kilauea, as we all know, was active just over a year ago and was very active and caused lots of destruction. Over 700 homes were destroyed from that eruption. So it is a very real aspect of our location, and one of the risks that we do run. Another feature of Mauna Kea is the weather. Most of the time it's very nice, especially during the summertime. It will be nice for weeks and weeks on end, and we'll get just pristine conditions for studying the universe. But in the wintertime, typically we'll get 2, maybe 3 big snowstorms come through, and we can get drifts of snow with 10, 15 feet deep. And we may be closed for a few days. Staff will have to go up and shovel the snow off the dome so we can open the dome and observe. Because oftentimes after these big storms, we get some of the best conditions for observing. Dry, very clear weather conditions. And so we want to get back on the sky as soon as possible. We have to get all this snow out of the way. And yes, there are snow plows in Hawaii, and we use them up on Mauna Kea. So about the only place we use snow plows. Haleakala on Maui can also get snow as well, and Mauna Loa as well. But Mauna Kea kind of takes the cake for the most extreme weather in Hawaii. This is a weather tower here showing a process called rime ice, which is when you're in a cloud and it's freezing and the wind is blowing and ice builds up on one side of a structure and sort of goes out horizontally. You don't want to be standing under this when the sun comes out and melts this ice and it starts falling off this tower, because it can be hundreds of pounds of ice up there coming down. So pretty dramatic weather sometimes, very dramatic. But then from down below, you have a tropical environment, and it's quite a contrast between the snow on the mountain and the tropical weather down below. In fact, there's one of the things that people do is try to surf in the morning, and there's actually been people skiing on the mountain, although we try to discourage that because it's not an appropriate use of the mountain to be skiing on the mountain. And this is what it looks like at night as we open up to observe the sky. And Andre Nicolai actually, I think, was going to say a little bit more now about what happens when the sun goes down and we start getting ready to observe the sky.
Yes, I'd like to share that part of the day with everybody, essentially, because that's a great illustration of how all that awesome piece of equipment has to work together, as well as an awesome piece of staff having to prepare so many things so we can open the dome at the end of the day and be ready for exploring even more, doing science that is only possible with 8-meter telescopes. So during the day, there's a team that works on all the pieces, making sure that everything is at the right temperature, everything is working properly, moving properly. And the dome itself is acclimatized for the forecast temperature when the night will start. So that means that when it's time to open, we can open everything all at the same time. And now the temperature inside the dome is already pretty close to the one outside. Yet we like to open when the sun is leaving, is almost gone at the horizon. So we have about another hour for everything to smooth out all the differences in temperature that might remain, and then everything must run. So in that time we have before we start the actual nighttime observation, so before the sun sets and when the night is dark enough, we have an opportunity for calibrating all the instruments, making sure that everything is in focus, making sure that we'll get the sharpest image when it's the first when we catch the first photons of the night. And the challenge after that is to use all the usable time of the night efficiently so we can achieve as many observations as we can until the sun comes back again.
Okay, thanks, Andre Nicolai. Appreciate that. The other thing that happens at this time of the day when the sun goes down and the vent gates open up and the observing slit opens up is that it often gets very cold. And the people controlling the telescope, like I said, are in helo. And so all of this is done remotely. And we have a lot of remote sensors that are keeping track of the environment, the humidity, the cloud cover, all of those sorts of things, so that if the weather goes bad, we can rapidly close things up. If the humidity, for example, gets above 80%, we close everything up because we don't want water vapor condensing on any of the optical elements. They do not appreciate that, and will bad things can happen if there's too much humidity or too much wind, even too. If the wind picks up and starts buffeting the telescope, at a certain point we have to close things down. It's not uncommon, at least once, maybe sometimes twice a year, for us to get winds over 100 miles an hour on the mountain. Andre Nicolai, did you want to add something there? I see your face.
Nope. Oh, no, I'm good.
Oh, okay. Okay, so let's move on and let's take a look at the telescope here from outside. This is kind of a trick photograph that we took, where we took multiple digital pictures as the dome was rotating and then stacked them on top of each other so it looks like the dome disappears. And so you can see the back of the dome, but you can see the telescope in front and what the telescope looks like compared to the size of the dome, and with the Milky Way up overhead. So we've seen what the telescope looks like as it's making observations. Let's take a look at some of the types of things that we look at. And this is my absolute favorite photograph that Gemini has taken. This is an infrared image of Saturn with its moon Titan down below at about 7 o'clock, 6:30, 7 o'clock position down there. And using a special technology called adaptive optics, we can essentially zoom in and see Titan, in this case, in exceptional detail. What we're looking at here is the atmosphere of Titan, and that bright spot you see there is a storm in the clouds of Titan. So we can see weather on a moon of another planet using this technology. It's called adaptive optics. And I want to talk a little bit more about adaptive optics. When you first hear of adaptive optics, it sounds very complicated. It's really not that complicated. I'm going to attempt to explain how adaptive optics works in the next 5 minutes. So We'll start with this rather simplistic view of starlight, or light from space coming into the atmosphere. When light is emitted from an object in space, typically there's essentially nothing that will interfere or cause any distortions to that starlight. The Space Telescope, being above most of the Earth's atmosphere, sees this light, and you get these basically parallel rays of light, waves of light coming into the Earth's atmosphere. And that's why observing from space is so powerful, because the light is not distorted by the Earth's atmosphere. As soon as those light waves enter the Earth's atmosphere, the air itself has different densities because it's different temperatures. Warm air is less dense than cold air, and it's mixing together. And when you fly in an airplane, you feel that. Basically, it's turbulence that you feel in the atmosphere. Well, that turbulence also distorts starlight and disrupts and bends that wave front, as it's called, of light. And by the time it gets to the telescope, it can be fairly distorted. That's also what causes the stars to twinkle. So the twinkling starlight is very romantic, but to astronomers, they hate it because it distorts our view. It makes the view blurry, basically. And so that's something that astronomers struggle with when observing from the ground, is the turbulence and the distortion caused by the atmosphere. So we have a way of addressing that, and it's called adaptive optics. Adaptive optics actually started as a military technology, where the military wanted to fire lasers up through the atmosphere, going the other way, looking out, and the atmosphere would distort it and cause the beam to spread out and not do any damage. And so they developed a technology that allowed the beam to stay very tightly focused and be adjusted so that the atmospheric turbulence wouldn't spread it apart. Well, when that became declassified and computers became more powerful and could do that routinely, astronomers adapted this technology for, again, what we call adaptive optics. And here's how it works. It actually uses a laser as well in this case. A couple of ways you can do adaptive optics: with natural guide stars, or with laser guide stars, or both. And we're going to show you how we make artificial stars in the sky to use this technology. The joke I used to make is that, or like to make, is that there's not enough stars in the sky for astronomers, so they have to make their own. And so for adaptive optics to work, you need to have a point source of light quite close to the object you want to study to use as a point of reference. So let's go up and take a look at how this works. We're going to propagate the laser into the sky. And so the laser is going to go through what are called relay optics on the side of the telescope. You'll see it here in a moment. There we go. It's going to go to the launch telescope on the top of the telescope, shine up into the sky about 90 kilometers up. There is a layer of sodium. That sodium was deposited by meteors in the atmosphere. Well, this is a sodium laser, and the sodium light excites the sodium atoms in the atmosphere about 90 kilometers up and causes it to glow. From our perspective back on the Earth, looking at that, we see a point of light. We don't see the column of light because we're looking at the column straight on, right? So we're going to go back now to the telescope and follow that beam down, that artificial star that we created up there in the sky. By the way, that star is bright enough to see with a small telescope, but you won't see it with a naked eye or even a good pair of binoculars. That light is focused by the telescope, and it goes down here into our adaptive optics module. Okay, this is our instrument cluster, and one of the instruments on there is the adaptive optics module. What it's going to do basically is process the light so that then we can study it and get incredibly sharp images of objects in space. So we're going to cut away the adaptive optics. Here comes that really slow-moving light. It goes through a collimator, a deformable mirror, a beam splitter is the third thing, and then the red light comes over onto a detector, and it goes to the computer, and we have an image of a star that looks awful. It's just twinkling and shimmering all over the place because we haven't turned on the adaptive optics yet. So the light comes through the collimator over on the left, and it's going to hit a deformable mirror, a mirror that changes its shape about 1,000 times per second. It's not doing it yet because the light comes down here to something on the bottom called a wavefront sensor. It figures out the shape on those wavefronts and tells that mirror to take that same shape but half the amplitude. so that when those wave fronts hit that mirror, they're flattened, like from potato chips to flat wafers. And then some of the light, the infrared light in this case, goes over here. Now that focuses on the detector, and look what happens to the star image. It goes from blurry and shimmering and going all over the place to a nice crisp image. And we can get, about a 10-fold increase in resolution by using that technology. And we can get to the theoretical limit of an 8-meter telescope, which allows us to out-resolve even the Hubble Space Telescope. The Hubble Space Telescope is a relatively small telescope compared to Gemini. Andre Nicolas, what, 2.4 meters across, I think, and we're 8 meters across. So we can collect more light, and with this technology, we can sharpen that light. There are limits to it. It's over a relatively small field of view, and it's at certain wavelengths of light that we can do this. But using this technology, we can do some pretty amazing things. This is what it looks like. This is an image that Joy Pollard took at Gemini over the course of a whole night. You can see over on the left, the sun is setting. Over on the right, the sun is rising. Way over on the left, you see that streak of light over there on the left, that streak of light, that's the moon setting. And then over the course of the night, you can see how the laser has traced paths across the sky as it tracks along with objects in the sky. And you can tell this is Gemini North. I'm sorry we can't be a little more interactive here on this, but you can because the North Star is right there in the middle, making a very small arc in the sky. The North Star is about a half a degree from being directly over the Earth's North Pole, but you can see all the circumpolar stars circling around the North Star due to the Earth's rotation. So let's talk a little bit more about some of the types of things that we see with adaptive optics. This is a wide view, what you might see with the naked eye, of the constellation of Orion. Those 3 stars in a row you may recognize as the Orion's belt. Down below that is a star-forming region called the Orion Nebula or M42. Let's zoom in a little bit. It's right there. We'll zoom in a little bit more, and you can see the Orion Nebula with a naked eye. You can see it with binoculars. A small telescope will show you an amazing view of the Orion Nebula. We're going to zoom in, though, with Gemini a lot. Okay, so let's keep going here. And we're going to take a look at a section of the Orion Nebula. And you can see in this image here, you see the entire Orion Nebula up in the upper left. We zoom into the nebula there. We zoom in one more time to this field right here, which we call the Orion bullets. What's happening down in the left there is that you have a star-forming region where very massive, what are called O-type stars are being formed. Andre Nicolas is a specialist in that field. He studies massive stars. And so maybe, Andre Nicolas, if you wanted to say a little bit maybe about what we're looking at here as we zoom in even more and what are called the Orion bullets.
Absolutely. So that's a very amazing image there, because Orion is the nearest young star-forming area from us. So for us, it's a great opportunity for really getting all the details of what's happening in that precise moment when you have massive stars being formed. And so in that area, you have a lot of very massive stars. They could be 20, 30, 40 times the mass of our own sun. And when a star gets that massive, as it forms and even later in its life, it loses a lot of mass in the form of winds. And those winds are very powerful. It's not just the wind like the one we experience here on Earth. It's not even the solar winds that you may have heard of. It's much more powerful and much more charged with particles. So everything around those stars have to cope with it. So what you're seeing here is the effect of those winds basically just catching those clumps of denser matter where other stars are being formed, and those clumps being just surviving this intensive wind from many, many massive stars. So there's a lot of dynamic, there's a lot of chemistry happening there. Those are very exciting areas that many people like to study for different reasons. Understanding the formation of the massive stars, their parameters, if they have magnetic fields, if they start spinning on themselves very fast when they're young, and all those questions that have a huge impact on our understanding of the life of the most massive stars in the universe.
Okay, thank you, Andre Nicolas. And Ironically, my wind chime is going off here as you were talking about those stellar winds. Um, that's not happening because of the stellar winds, by the way. So let's just take a quick look at some of the other recent findings from Gemini. By the way, all of the images that we're showing you here are available on our image gallery at gemini.edu, and go to our image gallery and you can find all of these images there, the videos as well. Okay, this is kind of a compelling looking image. It's very colorful. What's of interest, though, is the really boring small little dot at the very center. And you may have seen some stories on this. It was nicknamed the mini moon because it's the second known object other than our big moon known to be in an orbit like our moon is around the Earth. And actually by now, or actually I think it's early May, this object will have escaped the Earth's orbit and will be flying away from the Earth. But that little spot right there is only a couple meters across, a really small object that was discovered, and we followed up with it on Gemini. The reason the stars are so colorful in there, or those lights are so colorful, is those are stars, and this is a color picture of this object. But we had to, in order to get a color picture of an object with a telescope like Gemini, you have to take 3 different photos with 3 different filters, a red, green, and a blue filter, basically. And so when we combined it together, because they were taken at different times and this object is moving in the sky, it looks like the stars are moving, but it's really because this object was moving relative to the stars as we took those 3 images of this object to put it together into a color picture. And you can see the object itself doesn't look all that colorful. The stars do because they're separated and they're not all stacked on top of each other, but because this object, all of those colors were stacked on top of each other, and that's what it looks like when we do that. So, this was an object that was discovered, and we had to follow up very quickly because it was fading very quickly. And so what the astronomer did was to put in what's called a request for a director discretionary time. And so our director got the request to see this, and we rearranged the schedule so that we could get the telescope on this target and get that data quickly before it was no longer available. It's something called time domain astronomy, which is a very important part of modern astronomy these days, is following up on these objects that are changing very rapidly. And another recent finding, which is quite compelling, is of an object called a quasar. Quasars are very distant objects from the very early universe. And quasars are basically early galaxies with huge black holes in their cores that are glowing very brightly due to the black holes, which is the source of energy. And in this particular quasar, the astronomers were able to measure the velocity of those winds around that black hole from that material. And they measured the most energetic winds ever detected around a quasar. The winds are moving at about 13% the speed of light. And while they're not the fastest winds, the wind, this material has the most material there, so they have more energy because of the amount of material that is being accelerated to those incredible velocities. And so it's the highest energy wind quasar we've ever detected. And this is artwork, by the way. This is not; these are not actual images from the telescope. The data that they were using would be spectroscopic data, where they take the light and spread it into a rainbow of colors, and from that you can determine velocities of gas and objects in space. Anything you want to add, Andre, Nicolas, as the expert on these sorts of things?
Well, I think you've covered it very accurately. So if we compare those winds to the ones I mentioned before, this is like by many factors, about like many orders. Like I don't know if it's like 1,000 times more powerful, but it's in that range. You don't want to get anywhere near those black holes.
Sounds like a Star Trek episode, doesn't it?
Pretty much.
Okay. um, and also, we like to take pretty pictures too. And this is an image that was obtained with Gemini of something called the planetary nebula. This is a fairly compelling planetary nebula. Some planetary nebulas just look like donuts in the sky. Others have all these different shapes. But essentially, a planetary nebula like this represents the end state of a star of mass, stars of mass very similar to our sun. And so we think in about 4.5 billion years from now, our sun could end up in a similar state to this. Basically, it will expel its outer layers into space and become just an ember of its former self. Again, we've got 4.5 billion years before this happens. No need to worry. But by studying objects like this, we are studying the fate of stars like our sun in billions of years. And finally, the last pretty picture I want to show you is an image that we took of two interacting galaxies. Galaxies tend to form in clusters. And oftentimes these clusters of galaxies, the galaxies in the cluster will interact with each other as they're moving through space. In fact, if you've ever seen the Andromeda galaxy in our sky, it's about, I think, 2.6 million light years away. And I can't remember the number. Andre, Nicolas, you don't happen to remember how long it will be before the Milky Way and the Andromeda galaxy interact?
I think it's something like 2 billion or 2.5 billion years, but that's
it's a long ways off. But these interactions take millions of years to transpire. So it's like these galaxies are doing these graceful dances. And as they do that, they kind of tear each other apart gravitationally. But when galaxies collide and interact, it's not like throwing a rock against a wall or something like. They're not solid objects. Galaxies are mostly empty space. The distance between our sun and the nearest star is 4.3 light years, or I think about 26 trillion miles or something like that. Some incredible distance. So the galaxies really kind of pass through each other. The analogy is if you stand with a friend over a few feet away and you take two handfuls of sand and throw them at each other, most of the sand particles will kind of miss each other and just pass through each other. That's like galaxies. The stars don't collide together, but the gravity distorts them and causes these beautiful, intricate patterns over millions of years to form and evolve. And we can simulate that on computers and show what these forms might look like in these dances. But the timescales are so long that we can't watch it unfold on human timescales. So we can just sort of get a snapshot of what that interaction looks like right now. And this is a great example of two galaxies interacting. And one of the things that happens when galaxies collide is you get disruptions in the gas that cause stars to form. And that's what those red glowing globs are places where stars are forming in those galaxies, sparked by this gravitational interaction of these two galaxies. So, okay, I'm going to turn this back over. Oops, Andre, Nicolas, you have some slides, don't you, that you wanted to show? So I'm going to stop sharing my slides.
Yeah, and I will start sharing mine. So let me just first click. Okay, I'm sharing mine, then present. So as it slowly gets to presenting mode, is it going? Yeah, there we go. So you've heard it before. I'm interested into massive stars and also very young star clusters. So let me take the time to let you know what I mean by young star clusters. So here you could see an image. You can see an image of a young kindergartner class here. They are pretty similar to the group of stars I'm studying, in that sense that when you see a picture like that, you can really guess that they were all born more or less at the same time. So they all have the same age. Would that be a public school? That means they are, most of them, from the same area. So they all come from the same place. And if you see differences in between them, that comes from another reason than the age and where they come from. And that's very precious for us astrophysicists to have some certain values so you can work on those you don't know very well. So if I compare that group of young kids to the group of young kids I'm studying, so that's a young star cluster. What you're seeing here is the cluster called NGC 6520, but you see more than that. All the yellow stars in that picture are not from the cluster. They are background stars because when we look towards this cluster, we see a lot of stars that are also in a galaxy, but much further away. The ones that are from the cluster, you may recognize them very quickly. They are forming that kind of crown of blue stars around a yellow one. So that's what forms that group of stars. We know that they are fairly young. Actually, they are, in that case, they are 150 million year old. So I would say they're almost in high school at that age. To be very young, you would have to be a few million year old. That's like very, very young. You have to think that it takes about 1 million to sometimes even 5 million years for a star to form. So when it's in the first million years of life, it's very, very young. So most of them are blue, but right in the center, there's a big bright yellow star right there. And if they are the same age, and if they are at the same place, that tells us that there must be another reason for them to be different. And in that case, what happens is that the one star in the center was born with more mass. And that means that at the moment we observe it, so when we take that picture, it's already in the process of getting towards the end of its life, while the others are still shining blue, showing that they're still in the very earlier stage of their life. So by seeing groups like that, we ended up realizing that the total mass of a star at its birth corresponds pretty directly to the duration of its life. So the more massive the star, the shorter its life will be. And okay, we study, like in that case, that one cluster, NGC 6520. That's interesting. We can find a lot of things. We can study a lot of things. Orion, that we mentioned earlier, is another area where all the stars are the same age and in the same place. We can study the same way. But once we have many of them, then there's even more we can do. By knowing that they have the same age and they are in the same place, we can, for instance, find the distance between us and them. And that is very precious because here I'm showing a picture of the Milky Way. The Milky Way is the galaxy we live in. And I'm pointing with an arrow where we are, so somewhere around the sun. How do we know that our galaxy looks like that? Because this is not an actual picture. It cannot be an actual picture unless you live on another galaxy like M31, where someone, if there is anyone there with a telescope, could take a picture of us looking like that. But we don't have this privilege of looking at our own galaxy from outside. How can we know it looks like that? Well, the trick is to measure the distance to different types of objects in our Milky Way. And once we find them, we can trace them. So that would be, for instance, an illustration of all the groups, all the star clusters that we know about, and we know the distance more or less about. And then by tracing where they are grouped and where they are, and we can eventually then trace where the spirals are and where the star forming regions are. If we combine with that with other informations, then we can have a full picture of how our own galaxy looks like. And one thing I'm working on right now with a few friends from across the world is one of the latest Gemini discovery that we're about to send for publication in the month to come, which is another cluster that is even beyond where this arrow is pointing. So basically, most of the cluster we know about are pretty close to us. And the reason for that is because we have to look through our own galaxy. So there's a lot of dust and there's a lot of material in the way, acting a bit like a fog would do. We can hardly see through a fog, and the further, the harder it is to see. But there's one cluster that seems to be very young and very bright that we were lucky enough to spot all across our own galaxy after looking through the whole thing, through the center and through even all the other side of the Milky Way. And the interest in studying such an object is that it gives us information on a part of the galaxy that we know very little of. This big part here, which is in the center, is very dense, and it's really, really hard to see through it. So this illustration shows you arms going that way, but it's really what we can deduce from the little information we have about this area, because most of that here is almost terra incognita. So having access to a cluster on the other side with a determined distance and determined population, and eventually we may even be able to find what kind of chemical composition there is there, we'll be able to probe for the first time what's happening on the other side of our galaxy at the level of stellar population and stellar forming history, which is interesting because we can assume that if it happens here, it happens there, but the only way to know for sure is to see it. So that's a great opportunity for us. So that's in a nutshell what is occupying my mind for most of my time. Now I will shift gear. I want just to make sure that you know that we're using this very challenging times of confinement and social distancing, well, for helping out those that may appreciate the gist, is to share the designs of our card game. So for those who don't know, we've been printing cards and they play in a game that is very specific. It's a unique game coming from Gemini. And to make sure more people have access to it if they need to find something to do over their weekends, we're sharing the cards for printing. So if you go on this URL, you will find a place where it says download your own deck. So it's a collective game. Up to 4 people work together over a semester to observe and make Gemini work. The goal is to observe as many programs as we can. So programs are cards that look like this, and we observe those beautiful objects. This is featuring many of the amazing pictures we can take with Gemini, and we use Gemini instrumentation, and we have to go by the weather conditions. All the rules are also in that website. You go just a little under, you have the rule book, and of course there's a contact information if you have any questions about the game. I will stop sharing just to show what I did here. So you can print, about 6. I need to also stop my background, looks like. Otherwise, you won't see a thing. It will take me 10 seconds if you bear with me. Thank you very much. Here we go. So what I'm doing here, I'm showing 6 cards if you fit to printable area, and you can cut them to the right size for playing card sleeves if you already have those. So you can just, it doesn't have to be perfect. Once you cut them just so it fits in, then you can have playable cards. The recipe for how many cards to print and everything is on the website. I'm using some that have a colored back. There are different types of cards. If you can make different backs with paper to distinguish different types of cards. So all the recipes described on the site. I hope you can enjoy the game if you didn't have the chance to have your own deck already in hands. We'll continue to distribute the full cards as well, and we're in the process of producing new designs as well. But at least for now, everybody has access to the basic deck of 90 cards to play the game and learn how we operate Gemini in a fun way.
Great. Thank you, Andre Nicolai. And also, not to get ahead of ourselves, but you're looking at making a digital version of that in the sense that you can play online too, right? For the future. So stay tuned.
There are many people offering some help to transfer everything on a numeric platform. I know very little about those tools, but with the proper support, it should be doable. I don't know when, but that's definitely.
But for now, the printable version is available, and also there's a video that will help to with instructions. Yeah.
Yeah,
Great.
yeah.
Okay, I think at this point we're running a little bit over. However, I'm willing to stay as long as people want to stay online for if there are any questions. We'll open it up to questions if there are any.
Well, I'd like to first thank Dale and Harriet Dupuy, commenting from Louisiana. Thanks for watching, and thanks for your nice words.
And we won't keep you up too much later because it's almost 10 o'clock there, isn't it?
So Dupuy, Michaud, Chene, a lot of French names here.
Alyssa, did we have any questions from YouTube?
There are no questions right now.
I'm sorry?
There are no questions right now.
Oh, okay, okay.
Peter, I have a question.
Yes.
So can you hear me okay?
Yeah.
Okay. So I noticed when you were talking about the telescope and you were talking about how we do all of our observations from Hilo, you didn't mention also that there are special times when it can be run from the telescope up at the summit, as we used to do.
Okay, good point. Yeah, you know, we can run the telescope from the summit if we need to, and there are some observations that do require that we're there, but it's very, very rare.
Yeah. Also, and you probably would expect this from me, but well, first off, I'd like to say the part that you did on the adaptive optics was most awesome. But I didn't see, I wanted to see my laser shooting out of the telescope. We got some really great pictures from the south. We haven't utilized it very much here in the last couple of years, but I know there's some super pictures of going on sky with the laser.
Okay, yeah, let's take a look at what we can add.
So I was pretty charged about this. This was a great way of sharing Gemini. That's my feedback.
Okay, thanks, Jeff.
Okay, so we have some questions from YouTube now. Sunny Walker wants to know, in the photo of the stellar bullets, was that matter shedding from the stars or just background nebula?
That was actually being shed from the formation process of the stars as winds coming off those areas where the stars were forming. And actually, if you recall the picture, actually, I can go back and share that again. One thing that we didn't talk about there that's kind of interesting. Let's see if I can bring that up. Can you see that that slide again? There is a way to make a tracer annotate. Let me, wait a minute, let's see if I can get that to work. I don't see my mouse, but okay, I can't. It's weird because in this mode, I can't see my mouse, so I can't select the right cursor and all. So I don't even know where my mouse is right now. Oh, there it is. Bear with me here a moment and I'll get there. Okay, I still don't see anything on there. Anyway, if you look at these pillars that are going off towards the right, at the very tip of them, you see sort of some blue clouds up there. That's actually where there's iron in the cloud itself. And what's happening is that material in those clouds with the iron in it is being accelerated to such a velocity that it's causing the neutral hydrogen to glow, the hydrogen that's in that area that normally wouldn't glow. But as it's excited by these clouds passing through, it causes it to glow. And that's what you see as these sort of pillars going off to the left from those blue spots at the top. So it's kind of like a tracer on a bullet. And what's happening, though, is that cloud passing through the hydrogen excites the hydrogen, causes it to glow, and that's why we see that glowing pillar behind it, because that cloud is being propelled through that neutral hydrogen gas.
Okay, so we have more questions coming in on YouTube. Stargazer Girl 30 wants to know, how are observing objects chosen?
That's a good question. It's a lengthy process in time, and it involves a lot of people in the community. So when a big telescope like Gemini is built, it's with the goal of observing as many objects and getting as many data that will make progress in science as possible. And focusing on those that are really depending on the size of the mirror. And so we're having an 8-meter telescope. This is something that can do a lot of unique type of observations. So how do we select the targets? Well, it's not us to decide. It's for people to having ideas. So anyone who has an idea of something they'd really like to study in depth, thanks to the size of the big telescope, they fill a form that is made available to them, and they send that over to us. And once we, before a given deadline, once we gather all the proposals, all the requests all together, they are distributed in the community, and different experts will evaluate the value of the project. Some projects are clearly, very necessary to schedule, because we know that this will answer a question that we really need an answer for. Those that are really compelling, but sometimes may miss some details, just need to be reworked and proposed again. So with that process, we select a certain number of programs that are worth pushing over to the observatory. And once we have them, we prepare them in the system, and then we decide which one to observe and when. So the selection of merit is done. Now we're at the observatory. It's a given day. We have to decide what to do over the night. We go by deciding if the weather will comply. So we look at the predictions, and we try to plan for the most likely night. We also plan for other type of weather, but we focus on the one that is the most likely. Then we go for the objects that are available at that night, because there are some targets that are more visible in the spring, in the summer, winter, and so on and so forth. And then we go with the type of instrument that we have available. Some type of observation requires a certain instrument, but that instrument is not on the telescope yet, so we have to wait until it is available. So there's a suite of things to consider. So our goal is to grab, at the observatory, is to grab those programs that were selected as the highest priority from our peers, and give them the maximum chance to being observed at the telescope, and to use as much of the night time as we can use in the most efficient way.
Thanks, Andre. Next question, also from Stargazer Girl 30. What objects can Gemini see in the infrared that optical telescopes can't see?
That's excellent. So let's focus on those objects that are mostly for infrared. Well, why would an object be visible in infrared and not in optical? There's a variety of reasons. One is, well, because it does shine light in infrared and not so much in optical. So an example would be a star that is very, very small and not so massive. We call that substellar mass type of star, and those are brown dwarfs. We call them brown dwarfs. They have more or less the shape and the color of Jupiter, sometimes a little more maroon. They tend to be much redder, and sometimes so red that you really want to observe them in infrared, because this is where you will get the most light compared to optical, where they're not shining that much of the blue light, especially if they're far away. There are other reasons. Some objects would normally have blue light, but they are behind a cloud of dust. and the dust acts on the light by blocking the light, but it's blocking much more of the blue light than it is blocking of the red light. So the bluer the light, the smaller the wavelength of the light, for those that are familiar with the term. So it's like if the size of the grain is big enough for blocking the light. And as the light gets redder, the wavelength gets bigger, and then it's as if the light could go around the dust and go and shine through the dust. So there are many extreme cases when the dust is so dense and there's so much gas in between us and the object we're observing that we can only observe that in infrared and not so much in optical.
You can actually observe that phenomena when you watch the sunset, because as the sun goes down, it's going through a thicker layer of the atmosphere and there's more dust in the way. And so the red light can come through and you see the sun looking redder because that light can pass through that gas and dust, the same way the infrared light, even further into the red, can pass through the clouds of gas and dust that are obscuring it and at other colors of light.
Okay, thank you. We have a question from Ebony Marshall. It says, is the upkeep of sensitive equipment still happening while we all practice social distancing?
Yes and no. Yes and no in the sense that we are putting maintenance to the minimum, essentially because we do not want to be in a place when we have to urge people to go to the telescope, and would the spread of the virus be a big threat to the staff. Sending a group of even 5 people to go together in a confined place is not optimal. So to avoid having to send people to the summit at all costs, we don't want too many systems to run at the same time to minimize the risk of having one of them failing. In the South, so in Chile, they have decided to put everything to rest, completely to rest, with a very minimum use of energy and minimum equipment running. In the North, we can afford having at least our instruments cold, but not with no big moving parts, so nothing really happening. The reason why we do that is because if we have to go on Sky Quick, then we would be ready. In Chile, they would have to spend some days to put everything down to the right temperature and run. So it's a very minor difference, because in both cases, we're just making sure that we run to the minimum and to minimize the risk of having to do any maintenance. So it's almost as if you were at rest, but we're completely alive. We're just dormant.
I can just add a few details for those who may not be familiar. The instruments on a telescope like Gemini, we have multiple instruments ready to go at any time. And so they need to be kept cold with cryogenics and in vacuums, and need to be maintained at that level. Once you warm them up, it becomes a lot more difficult to then cool them back down again. And so we do have sensors that are monitoring them as well. Yeah, normally I think, and what the question was getting at was that these instruments are very sensitive, and they also require that they stay within certain conditions in terms of temperature and pressures and things like that. So yes, that is a very big concern.
That's it for the questions on YouTube Live.
We have a comment here saying that if it was not of the dust in our galaxy, the center of our galaxy would outshine the full moon. So this phenomenon of the dust blocking light is shaping the sky that we see at night. If it was not of it, the sky would look completely different. In the same manner, we could invert the problem and say if our eyes were seeing things different, nothing would look like what we see. So if our eyes were not seeing the optical light, so from blue to red, if our eyes were not able to see the colors of the rainbow as we see them, if they were seeing in radio waves, for instance, all the galaxies would look like a big continuous stripe of lights all connected, or Some stars would look pretty dim, while some things that we can barely see now would be super bright. If you were seeing in other type of lights, the whole world would look different. It just happens that we can only understand the universe from our viewpoint with our limitations, but that doesn't stop us.
Okay, sounds like a good place to stop if we're out of questions. And thank you everybody for joining us. And we'll be continuing these programs. Watch on social media for the, I think we'll do the next one next Thursday at the same time. Be safe. Take care, everybody.
Ahoy ho.